it is a big pleasure to have today with us Igor Klebanov. His connection with GGI is there from the very beginning, as we just said. He was a speaker to the inaugural conference. And so Igor Klebanov is a professor of physics at Princeton University and also the director of the Princeton Center for Theoretical Science, and is currently distinguished visiting professor at the Institute for Advanced Study in Princeton. And his research has been very influential on a number of topics in brain dynamics. He's done work which paved the way to the formulation of the ADS-CFT correspondence, the ADS-CFT dictionary, its higher spin formulation, large n-tensor models, matrix model approaches to studying the entanglement entropy in confining gauge theories. And today he will talk about strong interactions, color confinement, and strings. And I leave him to speak. Thanks,
thank you very much, Valentina, for the invitation and for the very kind introduction. Yeah, it's a pity I can't be there in Firenze in person, but I included a picture proving that I was once there. This is actually taken in Arcetri, very near GGI. So you heard the title, and basically I want to advertise the confinement problem as one of the unsolved problems, very major unsolved problem in theoretical physics, and its relation to strings. So let me start with a very broad introduction. Essentially, of course, everyone has heard of string theory. It's a very popular subject to talk about, argue about. It's very well known as the leading hope for unifying all known interactions, in particular the strong nuclear force, electromagnetic force, weak force, and even quantum gravity, the gravitational force. And all of this is supposed to connect into this grand consistent quantum theory. And some have even dubbed it the theory of everything, which is a kind of tongue-in-cheek term. But as is very well known, especially in Italy, is that string theory has had more humble beginnings. It was actually invented in the late 60s to model only the strong nuclear interactions. And in the last 20 years, this original goal of string theory has come into focus again. And it's still far from solved, this problem, but if we even make progress in this direction, that would already be very important. So let me talk a little bit about the history. So in the 1950s and 60s were the golden age for physics of hadrons. And then, so some hadrons were known before then, in particular the proton, but there was discovery of many, many new strongly interacting subnuclear particles. And the term hadron was coined by Okun, I believe, and it originates from adros, which is heavy in Greek, as opposed to leptos being light. So indeed, hadrons are much heavier than electrons. So the lightest hadron is the pi meson, which is around 140 MeV divided by c squared. And that's as opposed to electron mass, which is about half of MeV. And hadrons come in two types. There are baryons, which are protons, neutrons, lambda particles, heavier baryons. And then from the quark point of view, they consist of 3 quarks. And mesons consist of quark-antiquark pairs like pi, rho, mesons. So pi's are spin 0, rho is spin 1. Kaons are spin 0 strange mesons. And so just for fun, I included a bubble chamber picture of a discovery of charged K meson, which is decaying into three charged pi mesons. And of course, charge tracks curves, so they're easier to discover the charged particles. Okay, so what is the characteristic feature of strong interactions? Well, one is that they are indeed strong. They're much stronger than the next strongest force, which is electromagnetic. The strong interaction analog of the fine structure constant, which is G Young-Mills squared over 4 pi, is about 100 times bigger. And but they are, unlike electromagnetism, they're very short range. The typical range is about 1 Fermi or 1 femtometer, which is 10 to the minus 15 meters. And this short range of interactions is related to the confinement property, which I'll talk about later. So as more hadrons were discovered, they were grouped into multiplets. For example, here you can see the lightest spin pseudoscalar meson octet. And this gave impetus to the invention of the quark model by Gell-Mann and independently by George Zweig in the early 60s. And they basically started to model the substructure. They basically said that these hadrons are not truly elementary. In particular, the mesons consist of quark and anti-quark. And that was the beginning of the road to quantum chromodynamics and so on. But then there are also lots of heavier mesons with higher intrinsic spin. So in particular, here we have the vector mesons, the spin 1 mesons, which are K stars, rho, omega, and so on. And the earliest empirical evidence for the string-like structure of hadrons came from arranging either mesons or baryons into the so-called Regge trajectories, which are plots of angular momentum versus mass squared of the meson. And it's also known as the Chu-Fraudschi plot. And here you can see the leading Regge trajectory, which really does look linear. You see the first few masses lie nicely on the straight line. But then the difficulty with the higher ones is that they become rather broad. They decay faster and their widths get into hundreds of MeV. So it's very hard to pin down these higher spin resonances. Nevertheless, this type of plot is still perhaps the most convincing connection of string theory with the real world. Now, what about these other points? Well, they have higher mass squared. So we will see in a second that this leading Regge trajectory is just a kind of spinning string connecting a quark and an anti-quark. And these additional excitations contain also vibrations in addition to rotation. So then a big breakthrough was when in 1968, Veneziano, following his work with Virasoro, De Molo, Rubinstein, and others, proposed scattering amplitude for elastic pion scattering. In fact, I believe the history was that the first one was pi 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 omega, maybe. But anyways, it was very deeply rooted in hadronic physics. And by then there was this hypothesis of duality, hadronic duality, and people were hunting for an explicit formula, which was dual, so-called dual amplitude. And the Veneziano, this brilliant breakthrough guess was that this is just the beta function, the Euler beta function, which has this expression in terms of the Euler gamma functions. And alpha of S is the exactly linear Regge trajectory. Historically, this alpha of 0 is called the intercept, and alpha prime is called the Regge slope. So what's in one slide, what is string theory? Well, basically, we're dealing with extended objects. Well, in quantum field theory of point particles, we have a point vertex response where one, say, particle decays into two others. But in string theory, there is an extended, say, open string with two endpoints where we can think of quark and anti-quark as located. And then the splitting occurs somewhere in the middle of the string. So this is a diagram for an open string splitting into two open strings. And this is how, in the hadronic string interpretation, this is how a meson decays into two mesons. So this formula caused a big frenetic activity in the field. And pretty soon, Nambu and independently Nielsen and independently Leonard Susskind proposed the open string interpretation of this formula, which is shown here schematically. And so then people constructed, so this formula is for the 4-point function, but then people constructed higher point functions. But pretty soon some trouble appeared on the horizon. In particular, it was realized that the theory is truly only consistent in 26 dimensions, space-time dimensions rather than 4. And also there was a problem with the intercept. The consistent intercept was such that the lightest string state was at negative mass squared. So basically, while this model was beautiful, it was not exactly acceptable. But pretty soon people invented supersymmetric strings, and then field sort of went in a separate direction, eventually connecting with quantum gravity. But what about the true theory of hadrons? Well, not too long after this sort of first string formulation of relativistic string theory, what we believe to be the exact theory of strong interactions was formulated around 72, 73. It's called QCD, or Quantum Chromodynamics. It's a Yang-Mills theory with gauge group SU3. And the idea is that the hadrons are made of spin 1/2 constituents called quarks. And each quark comes in 3 different color states. There is an SU3 symmetry rotating them into each other. And moreover, this is a gauge symmetry. So it's somewhat analogous to the U1 symmetry for electromagnetism, but this one is a non-abelian in the sense that different elements of SU3 don't commute with each other. So the basic Yang-Mills Lagrangian here is the formula. It says trace F mu squared, which F mu has a formula, simple formula in terms of the vector potential, the non-abelian vector potential, which is a traceless 3x3 matrix. So they're rather analogous to electromagnetism, but was more complicated. And actually, Yang and Mills wrote down this theory for SU2 gauge group in the 50s, but they didn't have this type of color symmetry in mind. They were really gauging the isotopic spin. But later it came in, this formulation turned out to be the exact fundamental theory in a different way. Now, a very important feature of this theory is the presence of 8 gluons, which are mediators of the strong force. And actually one of the historic papers which is credited with formulation of QCD was by Gell-Mann, Frisch, and Leutwiler, called a case for color octet gluon. I mean, I think people were experimenting with different types of interactions, and they basically, it's a very brief paper, almost a conference talk, but very inspiring how one can make such a breakthrough. And of course, right around the same time, there was the realization that this theory is asymptotically free. And this resolved some experimental puzzles with deep inelastic scattering. So asymptotic freedom means that this alpha strong, or G Yang-Mills squared, at high momentum transfer, it gets smaller. And so this is alpha strong as a function of momentum transfer. And you really see the fall off of alpha strong. This is a picture from the Nobel website. This was, of course, the Nobel Prize to Gross and Wilczek and Pulitzer in 2004, but the work was done in 1973. And this really clinched the status of QCD as an exact theory of strong interactions, and there is plenty of experimental evidence. So even though the force is very strong, it gets weaker at high energies, and one can do perturbative Feynman diagram calculations with this theory. But the other side of this asymptotic freedom is what happens at low energies. And there, somehow these quarks and gluons are supposed to bind into the states that are really observable, but that's in some sense much harder to understand. You see that in some sense, this alpha strong actually blows up if you continue it at a special scale called lambda QCD. And there things get complicated and quote unquote non-perturbative. So what do we do? Well, that's where the confinement comes in. I mean, if you read these original papers, people were very puzzled. So suppose there are these color singlet gluons and color octet gluons and color triplet quarks. Why don't we observe them? What is it that prevents, in particular, these massless gluons from propagating? This was already a puzzle voiced in Young and Mill's paper. And something very interesting should happen. Basically, these massless gluons should not be able to live for a long time, and they bind into states called glue balls or things like that. So here is this claim millennium problem, which was formulated around 2000. I copied this from the website. It basically calls for a proof of the existence of a mass gap in the quantum version of Yang-Mills equation. Namely, if you even throw quarks away and just consider gluons, you don't see massless gluons as asymptotic states, you only see massive glue balls. And the status of this problem is unsolved. There is a more extensive sort of formulation for experts, which may itself be not the most up to date. I don't know. Right. So this is what I want to advertise. So right around this the new millennium, there was another. I want to mention a strings conference that took place in Michigan in July 2000, and as one of the gimmicks for the last day of the conference, Mike Duff, who was the local organizer, David Gross and Edward Witten, formed a panel to select the best 10 problems for the new millennium. And this was a pretty memorable day. I mean, most of these problems, this website still exists and you can look up what these problems are. I mean, most of them are really grand questions, like how do we explain the fundamental constants of nature? Why is the cosmological constant 0, and so on. And if you look at these problems, actually, none of them are really solved. Maybe the closest, the one where there has been the most progress is the black hole information problem, but even that is still not fully understood. But so coming in, just squeaking into this list at number 10 was this very banal question that I submitted and independently Oyvind Tefjord. Basically the same question: can we understand quark and gluon confinement in quantum chromodynamics? Okay, but since then there's been, not that much. So I want to talk a little bit about the progress since then, and just how I would formulate this confinement problem, or how most people would think about it. So I think most people would think about it in terms of lattice gauge theory. So as Wilson taught us, this is the fundamental non-perturbative formulation where you have these, so if you look at the Euclidean lattice in for, say, 4 dimensions, for each plaquette, we associate a term which is a trace of the product of, say, SU3 matrices around this plaquette. So this is a very simple and natural action. And then one can try to solve it on the computer or develop various expansions. So one thing that this taught people right away is that if you just expand that strong coupling, namely you just expand in this plaquette term, then the confinement is rather trivial and appears right away. The confinement is the area law of the Wilson loop. Namely, if you think of this big Wilson loop, which is trace of the product of U matrices around some big loop, and you can think about it as the amplitude for, say, a quark and anti-quark to be created here, separated by distance L, then propagated in time by time t, and then reannihilating somewhere here. And then, so what Wilson taught us is that if the log of this expectation value is proportional to area, then there is confinement. This basically corresponds to the fact that the potential between quark and anti-quark is going to be linear. It grows at large distances as the distance between quark and anti-quark. This is a huge difference from what happens with the Coulomb force in electromagnetism, right? So that's the new feature, is this linear potential and the area law for the Wilson loop. And how do you see this area law? Well, basically, to make this expectation value non-vanishing, you have to tile this big loop with the number of small loops such that their number is proportional to the area. And then say so you pick out the minimal number of terms to make this non-vanishing, because just the integral of du over the group of u is 0. So you have to balance out these links. And this means that you tile the entire big loop with small loops. So you get area law in the strong coupling expansion very easily. But the problem is that to reach continuum limit, you in fact want to make G very small rather than large. So instead of strong coupling expansion, you need weak coupling expansion. And this is really due to this asymptotic freedom phenomenon, that at short distances, when the lattice spacing becomes small, this G becomes of order 1 over the logarithm of A0 over A, where A0 is a characteristic UCD scale. So you have to, as often happens in physics, there is sort of one expansion, which is easy, but then you have to go all the way to the other side from weak to strong coupling. And this is one of the difficulties of proving confinement, is how do we know that as we extrapolate, this color confinement does not disappear? There is no phase transition in the process of going from strong to weak coupling. So the numerical simulation strongly suggests that the answer is no. And initially they were on small lattices, but now more recently we can access lattice sizes up to 100 in each direction. And the results look very convincing, especially for pure glue theory without fermions. But there is probably still, it's fair to say that there is still no mathematical proof of confinement. So here is what one sees from the lattice results. You basically put a static heavy quark on one somewhere and the heavy anti-quark somewhere else. And then you see formation that the action density or energy density gets collimated into this UCD flux tube from an electric flux tube. And this characteristic thickness does not vary much with the distance. It only varies very slightly logarithmically. And the thickness is of order Fermi. Again, this characteristic scale of the strong interaction. So from the lattice, we see rather clearly the formation of this UCD string, although it doesn't seem like an elementary string. It's a kind of thick string. Nevertheless, if you go to distances between quarks much bigger than 1 Fermi, it appears that the dynamics of this string is well described by the by the Nambu-Goto area action, but with important higher derivative corrections. So while the elementary string, which let me just go back. So this sort of original Nambu-Goto string was just described exactly by the area action. But this QCD string, you also have interesting corrections. But in some sense, the two should be fairly closely related. So I think it's fair to say that strings, so people often complain that strings have nothing to do with the real world, but we certainly have observed strings in numerical simulations of Yang-Mills theory. And in these papers, people routinely talk about measuring string tensions and various other quantities related to the string. By the way, if there are questions, feel free to interrupt. If there are any questions or comments. Okay, so let me go on then. So this picture. So now we can take this flux tube or QCD string and consider what happens when the quark and antiquark just spin with some angular momentum. And then it's a simple calculation to figure out that this indeed gives this linear Regge trajectory. Namely, the spin is a linear function of the mass squared. And the mesons, therefore, are identified with excitations, rotational and vibrational, of this string. And the actual energy density of this string is of order 1 GeV per Fermi. Again, these are typical units for strong interactions. In SI units, it's 1.6 kilojoules per centimeter times 160 kilojoules per meter. So it's if we could harness this energy, this would be a good thing. So now, and here is again a plot of this Regge trajectory starting with the rho meson. So this is the isotopic spin 1 Regge trajectory starting with spin 1, and then you have spin 2 and so on. But the problem is that these strings actually can snap in the middle. In presence of dynamical quarks, they snap in the middle, and that's how mesons really decay. So this kind of makes the problem even harder, and maybe the linearity of this Regge trajectory does not stare at us in the face. But there is soon after the formulation of QCD, 't Hooft proposed there was another big breakthrough, which is the generalization from 3 colors to n colors. And this generalization is precisely good for suppressing splitting and joining of this string. So this problem many of you have also heard, that if one takes the large n limit while keeping the so-called 't Hooft coupling, which is G Yang-Mills squared times n fixed, then the probability of snapping the flux tube by quark-antiquark creation is really 1 over n. So this allows us to dial the string coupling. The string coupling is a coupling of 3 strings together, and one can make it weak in a large n theory. So one obvious remark is that if we lived in a world where n was, say, not 3 but 33, then no one would ever criticize string theory or doubt its relevance, I think, because then this leading Regge trajectory would go on to much, much higher spin. These higher spin states would be much narrower, and we would be very accustomed to the string picture of excited mesons. But in the real world, it's sort of right at this murky boundary where you can see a few of them, a few excited string states, and then it all gets drowned in this complexity of strong interaction. So, but theorists, of course, find it very useful to think about this large n limit. It's not just a theorist tool. In phenomenology, it's been very important. And this led to many nice things. And in particular, it led to, so one of the biggest sets of progress in relations between gauge theory and string theory has been the ADS-CFT correspondence. And this originated very much from thinking about large n limit. if we didn't know about large unlimit, we probably would never discover the ADS-CFT connection. So how did it come about? Well, Polchinski in particular realized in the mid-90s that D-branes are important states in superstring theory. D-branes are objects where open strings can end. So even if we have a closed string, it can touch this D3 brane and open up and sort of slide along the D3 brane. This is shown in this picture. But then if you stack many of these D3 branes, a large number, n of them, on top of each other, on one hand, this realizes the maximally supersymmetric SUN gauge theory, but it also creates a particular curved background of 10D theory of closed superstrings, because this becomes a basically high tension object. And the metric of these three branes has a very simple form shown here. These are the 3+1 longitude directions along the brane, and these are the 6 dimensions around the brane. And then it's a very simple exercise to take this limit of small r and show that this actually approaches at small r this so-called throat or ADS 5×5 region. The presence of the 5-sphere is easy to see. This is the 5-sphere metric. And this r squared gets canceled by 1 over L squared over r squared here. So you get a sphere of very large radius L. And the very amusing thing, which makes it all fly, is that the radius of this sphere becomes large in string units when 't Hooft coupling is large. So you basically get a theory amenable to the methods of Einstein's general relativity. And one can develop expansion and inverse 't Hooft coupling for this theory. So this kind of crystallized in the late 90s. And now we have a more general picture that, so this particular theory, this maximally supersymmetric SUN gauge theory, is special because in it there are additional massless fields that completely cancel out the asymptotic freedom. So it's an exactly conformal gauge theory. The coupling in it doesn't run. And one can make this coupling large, and then we get a weakly curved 5-dimensional anti-de Sitter space times weakly curved sphere. And this is a kind of picture. Usually you see this is a picture of the hyperbolic space or negatively curved space. It's from a kind of semi-popular article that Juan Maldacena and I wrote. You often see these fancy Escher diagrams, but we decided to tile it with cows to stress the fact that this model is a spherical cow. Spherical cow is probably many of you are familiar with this joke. It's just another way of thinking of naming idealized toy models, right? It was a joke about a physicist who was supposed to help out on a farm with milk production, and after 3 days he walked in with a brilliant idea. Let's consider a spherical cow. It's not a particularly funny joke, but so here we have this, we wanted to call it hyperbolic cow because cow is tiling hyperbolic space. And you see that that there are many cows around the perimeter. So it's a disk, but its physical circumference is really divergent. So this is just a 2-dimensional hyperbolic space, and higher dimensional works analogous. Okay, so this is so it's a very beautiful symmetric space, and one can do perturbations around it. So the idea is that when n is large and when this 't Hooft coupling is large, you have things under control and figure out a lot of interesting things about the behavior of strongly coupled gauge theory. Although it's not QCD, of course, it's a kind of cousin of QCD. So in particular, we can develop expansion in the natural expansion when we include higher derivative corrections to supergravity, that will give us terms which are 't Hooft coupling to the negative powers. And this complements the usual weak coupling expansion and positive integer powers of lambda. So there are two different, this gives us a totally new way of expanding this large N theory. And there has been considerable success in showing that these two expansions really meet in the middle. But it's still, again, not fully proven. So this duality has passed, this ADS CFT duality has passed many checks, but still no proof. But now, so one thing that you can complain about is that this is not a confining theory. It's not, it's a theory where the coupling doesn't run at all. Nevertheless, one can do some, so let me describe one interesting calculation, which is the computation of entanglement entropy. This is an object that has been studied extremely well in the last, dozen years. The idea is that to partition Hilbert space, say, into A and B, and then one derives the reduced density matrix, which is a trace over B degrees of freedom of the vacuum density matrix, and then calculates the von Neumann entropy minus trace A rho log rho for the A region. So what was discovered early on is that in typical local QFT, there is the leading, this entanglement entropy has area law. Basically, it's if you partition, say, three-dimensional space into a sphere, inside and outside of a sphere, there is the area of the sphere divided by UV cutoff squared. This was discovered by Mark Srednitsky quite long ago. So a very nice thing from the point of view of this new ADS CFT correspondence is that there is a natural geometrical prescription for computing the entanglement entropy. So if you have, like, this is our boundary, and you have, say, regions A and B, which is inside and outside of this sphere. Here it's shown as a circle. Then one needs to find a surface that's going into the extra dimension, the extra sort of fifth dimension, and compute the area of this surface. And this turns out to work very well and give us results in agreement with expectations, for example, in 1+1 dimensions. And it gives us a lot of valuable predictions about behavior in more than one spatial dimension. So now I want to talk a bit about how to make this theory confining. So how do we know? First of all, let's go back to the pure ADS theory. This one has this extra, so ADS 5 corresponds to four-dimensional confining, four-dimensional conformal theory. And there is this extra coordinate Z. You can think of our space is located at Z equals 0, sort of on the boundary of the ADS space. And there is a nice prescription due to Maldacena and independently Ray and Yi, how to compute the quark-antiquark potential. It's sort of similar to this prescription. You draw something on the boundary and then extend it into the bulk. And this, so you want to find the shape of the string connecting the quark and antiquark located on the boundary. In the case of pure ADS space, it gives exactly Coulombic law because it's a scale-free theory. So it's 1 over R both at short and long distance. But there is, one can imagine a way of modifying the geometry so that this Coulombic law is only there at short distances, but at long distances becomes confining. You need to modify the metric at large Z to introduce some kind of infrared wall. And this was first pointed out by Polyakov as a kind of general approach to confinement. So if the space ends at some maximal value Z, where the warp factor A is finite, then the string will just sort of lie down at this infrared wall. And then we will get a confining string of finite tension. It will, it will not lose its tension. So a few years after that, Strassler and I found a somewhat complicated supersymmetric version of the theory, where this is exactly realized. It's only minimally supersymmetric. It has n=1 supersymmetry, and it involves some arrangement of d-branes on a nice space called the conifold. The conifold is sum of z squared over 4 coordinates z equals 0. But we realize that if you add certain wrapped branes, then the theory actually generates a scale by itself. It kind of implements dimensional transmutation, and the conifold becomes deformed. And basically, as a result, you get a curved space, which is a dual of a confining gauge theory, which is, on one hand, it's logarithmically running in the UV, and it's confining in the IR. And so when you do the calculation in this theory, for example, of quark-anti-quark potential, you do find that it's coulombic at short distances, but then makes a transition to linear potential at long distances. And this is just what we want to happen in QCD. So this is a kind of toy model of confinement. This is actually a plot from the lattice, a rather old plot, and you can see nicely this transition from coulombic to linear force at distance scale around half a. Okay, so let's take stock of what has been done. So there are a couple of somewhat similar models from gauge gravity duality, but nothing like QCD in the end, because it turns out that it's really difficult to describe asymptotically free theory. Nevertheless, I think these toy models of confinement did teach us something. So for example, if we apply the Ruta-Kayanagi prescription for computing the entanglement entropy, which I showed here, and apply it to, say, the entropy of a region between two planes and outside of these two planes, it's a rather simple calculation, which back in 2007, I carried out with Murugan, my student at the time, and David Kutasov. And we found that there is a kind of phase transition in the entanglement entropy. Namely, at short distances, the entanglement entropy is large. It's of order n squared and comes from the color degrees of freedom. But then at long distances, basically it becomes of order 1. The term of order n squared becomes 0. And this suggested that something similar should happen in actual, say, QCD. And indeed, on the lattice, people did observe this sharp drop in entanglement entropy at the characteristic scale of, again, half a Fermi. You can see this from the lattice plot. So in this sense, this entanglement entropy can be viewed as a order parameter for confinement, deconfinement transition, but just at 0 temperature. Here, what you're varying is just the size of the region rather than temperature. And I feel that it would be very interesting to study the role of entanglement entropy in lattice QCD in more detail. Okay, so now I will just say a few things to end my talk. Basically something I've been doing recently, but so what have we learned from gauge string duality since 1995, 96? We certainly learned a lot about CFTs, conformal field theories. We even learned something about confining strongly coupled gauge theories. And it provided us with a physicist's proof of confinement and ability to calculate, say, global spectrum in some exotic gauge theories like the one that I described, which is dual to this deformed conifold. But yet we still don't have a quantitative handle on the asymptotically free series in 3+1 dimensions. If you remember, starting from the lattice, our goal was to take coupling at lattice scale to be small so that we can see the asymptotically free regime. And that turned out to be so far extremely hard from the point of view of the gauge gravity duality. So as a modest step, we can try to draw back to some 1+1 dimensional models and maybe get some other types of intuition about higher dimensional dynamics. And one model that probably many people have heard about is the Hopf model, which is just a two-dimensional version of copy of QCD, where you take 2D SUN gauge theory coupled to NF fermions. And what Hopf showed is that it's exactly solvable in the large N limit if you use light cone gauge, A minus equals 0. It's quite a beautiful solution. There is then a single Regge trajectory of mesons, and the masses are obtained by solving a simple singular integral equation, which, while analytically it's still not solvable, it's very simply solvable numerically. And this is a plot from Hopf's paper. You can see this Regge trajectory for m equals 0. And then as you increase m, just masses shift a bit. So this model has been used many, many times, but it does not really, in some ways, it's not much like higher dimensional QCD because it does not have local adjoint degrees of freedom. Because all that the gluons do is they provide a linear kind of potential for connecting quark and anti-quark, and that's why this phi of x is basically the light cone wave function for the quark and quark pair, where x is the momentum fraction of the quark. So how can we complicate this to the Hopf model to make it closer to real world? And this actually also goes back many years, but I started working on it almost 30 years ago with Simon Daly. We basically said, let's take 2D QCD, but add some matter in the adjoint representation. For example, we can make it a scalar, or even simpler, it turns out to be an adjoint Majorana fermion, which we can view as a toy gluino. This theory has particularly nice properties. It's super normalizable, has non-trivial vacua and the mass gap. This is the Lagrangian for the action for this theory. There is a massive one adjoint Majorana. Recently, there has been some new activity on this theory, which made me go back and think a little bit about it again. And in particular with my colleague Silvio Pufu and his graduate student Ross Dempsey, we wrote a paper where we basically, in addition to this adjoint Majorana, we added NF fundamental Dirac fermions. So it's a kind of souped up version of the Hopf model. Namely, you still have these fundamental quarks, and then they can be connected by strings. But now the strings can have any number of adjoint quanta sort of embedded in them. So these strings are now dynamical, kind of, and now you have an infinite number of Regge trajectories, and the model starts looking much more like a higher dimensional version of QCD. So, but then this theory actually has an interesting surprise that the tension of the string connecting quark and anti-quark, naively it's non-zero, and it's of order g squared, because in 1+1 dimensions, the Yang-Mills coupling has dimensions of mass, so the string tension is just g squared n. But and this is what happened in the Hopf model. That's why you have these linear Regge trajectories. But in this model, the string tension can actually get renormalized to 0 when these adjoint fermions are massless. So then what happens is that if you look at the QQ bar potential at short distances, it starts out as linear, but then it flattens and becomes exactly flat at long distance. Now we can't prove this, but the calculations we've done are completely consistent with this picture, that the massless adjoints renormalize string tension to 0. This actually was already conjectured in a paper by David Gross, Lattice and Smilga and I in 1995. And then recently, this theory was revisited by Komargodski and collaborators, and they used some fancy techniques called non-invertible topological lines to also argue for 0 string tension in this theory. But clearly a lot remains to be done. I mean, we did some more light cone spectrum calculations, which clearly show that there is no confinement when the adjoint mass is 0, but you regain confinement when there is a small mass. And this way you get a kind of model of weak confinement where instead of exactly flat, you will have just slightly sloping linear potential. Okay, so now I'm basically done with the talk. So I've gone through, a bit of early history of hadronic physics, and it's how string theory was born. But now I think the QCD certainly looks like a complete theory of strong interactions. It's a beautiful theory which is sort of self-regulating by being asymptotically free. It's a theory that is completely consistent on its own, and we want to understand its properties, in particular the confinement in this theory. But what this 1 + 1 dimensional example taught us is don't take confinement for granted. So even in 1 + 1 dimensions, where you would say that the potential is just obviously linear, it can be renormalized to 0. So, and this is where sort of the danger lies, that somehow as you go sort of from strong coupling expansion to weak coupling expansion, something could get renormalized a lot. And for these reasons, proof of color confinement in 2 + 1 and 3 + 1 dimensions would be very important. And also it would probably improve connections between so-called QCD strings, which we saw in the lattice pictures, these fixed strings and fundamental strings. The gauge gravity duality gave us some way of connecting them, but we certainly need to do better. And hopefully this can give new analytical insights and approximations to real world spectra of hadrons and multi-string tensions. But one new thing, these problems are certainly old, but now lattice gauge theory, I think, is going through a period of accelerated development. There are many new techniques related to machine learning and so on. And in particular, there are groups working on extrapolation to large N and finding very interesting results. So I think I'm quite optimistic that if we go back to the confinement problem, we can learn a lot more, both about string theory and about real world.
Thank you very much for this great talk. And I see already there is a hand raised. Alvaro can also speak if it's you, so you can unmute.
Yes.
Thanks.
I have a comment, which is one fun possibility of what you said towards the end is that quarks and gluons actually are not confined. And there are states, very heavy states, of liberated quarks and gluons. Of course, you don't believe in that, but it's a fun thing to think about.
Yeah, I think, I agree that we shouldn't take anything for granted. We should probably just start working from first principles. I mean, one actually very interesting thing that's happening now is the discovery of all these exotic hadronic states. In particular, there was a quite recent announcement of this tetra quark, which is very narrow. So people are actually seeing just from experiments some new zoo of particles. And that may teach us also about confining forces. Yeah, I think what you said is a little bit realized in this 1+1 dimensional model, where you surprisingly can screen a fundamental charge by adjoint charges, massless adjoints in some sense. That's basically was the point of my talk. So I don't think this can happen in higher dimensions, but at least here we do see this type of renormalization.
Thanks.
Thank you. There is a question from Alejandro Cabrera, who thinks that some people criticize that what some people criticize about string theory is not so much its role in effective descriptions as presented by you in Lattice QCD at the beginning of the talk, but its fundamental ontological nature, and whether you have some comments about this criticism about the fundamental and ontological nature of string theory.
Well, I think that, I mean, certainly superstring theory in 10 dimensions, it looks like a theory that definitely exists in the theoretical library of theories. I mean, what is less clear if this is the definite path to the theory of everything, to unification of interactions. I mean, people have invested a lot of effort into studying this theory and discovered a lot about the supersymmetric world, right? There is a supersymmetric world of BPS black holes and so on, and the corresponding mathematics. So to me, it's not a worry at all that string theory is a great theory to study. I think what is less clear is what happens, how you break supersymmetry and really connect it to the non-supersymmetric world. And recently, I would say the worries are increasing that maybe we're missing something about the fundamental formulation of string theory as we know it. And in this sense, this QCD string is mentioned as a nice bridge, because that string theory certainly does not require supersymmetry. It's by definition stable without supersymmetry. It's the one example that's often quoted as definitely a consistent and stable example. And if we understand it more in the intrinsic string theory terms, that would sort of be interesting to both sides, both QCD side and the side about the fate of string theory.
Perhaps I add, but to which extent you can get a quantitative understanding of confinement from this QCD string project, let's say, you think? Because as you mentioned many times, the lattice results are there. And so in other words, solving analytically the confinement, of course, we can learn a lot, I guess, but quantitatively, do you expect something more?
No, I think people who study the long string sector, namely, suppose you take your lattice theory and have many points in one direction, and then consider, say, a long low string wrapped around that direction. People on the lattice can study its spectrum, like the so-called fine structure of the string, and they can match to string theory. Then there are various higher. So then the question is, what is the world sheet action for that string, right? The leading term is the non-Bogota string, non-Bogota term, but then there are higher derivative terms, and this definitely is. People are making progress in matching them. You can just hit the coefficients, the structure, what you see is definitely working. So this long string sector, I think, is a very safe sector for testing this interplay. What is much harder is the small vibrating strings that describe the glue balls. For them, it's much harder to say that we can use this QCD string to describe the details of the glue balls.
Thank you.
That would take, it's not clear how to do it at the moment. But people are definitely studying, for example, multi-wrapped strings, comparing with what we know from gauge theory, like from, string gauge comparison.
Glennis Farah, please unmute yourself.
I think I'm unmuted. A lovely talk, Igor. Could you talk more about the dimensionality dependence of your intuition about confinement? I mean, one might have, so after all, the string in lattice gauge theory that one sees and that you were talking about is a one-dimensional string. And so how does the extra dimensions affect it? Do you have an intuition about how, why the two-dimensional case so you said that you thought that was going to prove not to be representative. As higher dimensions, you would have confinement. I just wondered if you could just expand on that whole question.
Yeah, thanks a lot for asking that. I should have said more clearly. Yeah, I think that most people would say that in 1 + 1 dimension, there is no particular confinement problem, right? Because just perturbatively, the Coulomb force is linear. So just perturbatively, you get confinement. The problem becomes more tricky already in 2 + 1, right? Because then it's already non-perturbative there, because the G has dimensions of square root of the mass there. So the string tension will be over G⁴. And so, yeah, I think the specific mechanism for confinement is probably rather dimension dependent. The one model where so in 2 + 1 dimensions or in 3 Euclidean, we know through the work of Polyakov that even compact QED is a confining theory. And there the detailed mechanism is understood. It's basically the instantons, which are, people call them the monopole instanton. The magnetically charged instantons essentially prove confinement for compact QED. And then there are various mechanisms in 3 + 1 dimension. So it's rather a dimension dependent story. I flashed this final example with 1 + 1 dimension just to illustrate the fact that even when confinement may seem obvious, it can actually wash out through some unusual effects. And these 1 + 1 dimensional models, most people would say, oh, they're not that interesting and a lot already is known about them. But now people are actually working pretty hard on mapping out the different vacua. Like even this model with a single Majorana joint has turned out to be very tricky, very, very tricky. It has, in particular, it has these different, as Witten pointed out in 79, it has these discrete theta vacua, which is really like you can, maybe this I can say also. Yeah, when you look at this 1 + 1 dimensional case, you can put some number of, say, anti-quarks at -infinity and the corresponding number of quarks at +infinity. And this number, K, can range from 0 to n-1. So you get n different topological sectors corresponding to this fundamental flux. And this Witten pointed out in 79 as a discrete analog of the theta angle. So, but then more recently, people realized that in the continuum limit, there are many more different topological sectors related to these non-invertible lines. So even these simple-looking 1 + 1 dimensional theories are tricky. And moreover, the theory with the single Majorana is very hard to simulate on the Euclidean lattice. It seems impossible. So now I'm actually thinking about the Hamiltonian formulation of this theory just on a spatial circle. which doesn't seem to have obstacles. But so just even in the world of 1 + 1 dimensional QED, there is a lot of QED and QCD. There is a lot of activity also relating it to atomic physics. So if we don't solve confinement, we could actually connect to something that can be seen in experiment.
Thanks a lot. Also for the question, there is a question from Giampiero Passarino. You want to solve confinement, a non-abelian problem. Could you explain the properties of a crystal starting from QED, an abelian problem? Thanks, from Giampiero Passarino.
Well, this is just matter. Yeah, it should be more of a question to a condensed matter physics. I thought this is pretty well understood. I mean, just but I'm not the greatest expert. I mean, sort of goes back many years how we think about. Well, at least once we assume the existence of a crystal, we can study its vibrations, phonons, and so on. And it's a vast field of condensed matter physics and materials. To me, it seems like it's pretty well under control.
All right.
Yeah, one question you can ask is, say, the corresponding question would be, can you explain large nuclei or even infinite nuclear matter, starting, say, from QCD? And that, of course, also there are thousands of papers being written on that.
The question was made more precise by Passarino, saying only using QED, so only using an abelian starting point, whether you can maybe.
Well, if you just assume that there are charged, that atoms consist of charged nuclei and electrons, I think so. I mean, there is still remaining question of how nuclei are made, but I would say yes.
Okay. If there are other comments, now is the time for questions. Probably we exhausted all the questions.
Yeah, it's quite late for you, right?
Well, no, it's also for you. You have to have lunch, I guess. No, it was really a pleasure. And yes, we want to thank you again for this great time together.
Thank you so much.
Yes.
Yeah, and
thank
it
you
was great
again.
to get these ideas, try to get them across. Yeah.
Yes.
Thank you very
that
much.
was successful.
And, please send us your slides, the file of your slides, and we will publish it.
Yes, yes. Yeah, I can send a PDF file with the slides.
Great, great. Thank you very much.
Thank you. Have a great evening.
Thank you again.
Wherever you are.
Yeah, thank you very much. Thanks.
Thank you.
Bye.
Thank you. Bye bye.
Bye. Bye.